At Earthscope, we're working on what we call the Cloud On-Ramp project, which is creating resources to help the geophysical community take advantage of new capabilities as the NGF data archive becomes increasingly cloud optimized. But we're not the only organization in the geosciences doing something like this. So learning from others, collaborating with them has been incredibly useful in this project. And so for you, dear viewer, and the rest of the community, I thought it would be interesting to learn a little bit about one of these other projects, or two of these other projects that have benefited their user communities already. It might give you a sense of like where we're trying to go. So to that end, today we have Amy Barchauskas of Development Seed here to tell us a little bit about NASA's MAP and VEDA projects. So Amy, thank you for sitting down with me here.
Yeah, thanks for having me.
So let's start with those projects. So tell me a little bit about VEDA and MAP. Who are these user communities and what kind of data archives are we talking about?
Yeah, absolutely. So I guess to start out with, NASA is doing something, I think, similar to Earthscope in the sense that it's recognized that it was going to have an explosion in data volume and decided to migrate its Earth observation data, a lot of its Earth observation archives, to the commercial cloud, so specifically AWS, because it knew it needed to be able to scale to a larger set of users and a larger set of data. So now we have like parallel access from anywhere to a lot of NASA's high value data sets. A lot of the data has already been migrated. So wanting to sort of demonstrate like the utility of this, one of the projects that NASA initiated was the Multi-Mission Algorithm and Analysis Project, or MAP, M-A-A-P. And so the MAP project actually predates VEDA. So MAP started around 2018, and its mandate, in addition to sort of showcasing the power of moving the data to the cloud, was to specifically support above ground biomass scientists with moving their algorithm development to a cloud-based development environment, what we call the algorithm development environment. Having those biomass researchers move their workflow onto that cloud-based hub so they'd have direct access to some of these data sets now hosted in the cloud. So that was one of the goals there with MAP, as well as to support NASA actually collaborating with ESA, which is trying to do something similar. So the European Space Agency wanted to do something very similar. So MAP was also a place for us to basically, within two separate sort of scientist communities of ESA and NASA, sort of come together and say, hey, what are you trying? How are you hosting data? How are you creating a hub? How are you sharing algorithms with each other? So yeah, when I started at Development Seed, I started working on that project, and it's still around today. It was successful in basically helping the biomass researchers in scaling their algorithm development globally, as well as it's supported some fire perimeter algorithm development and scaling that as well. And based off of the success of that platform and some other interests of NASA in basically supporting Earth observation, development in general, we decided we came up with this idea of VEDA. And VEDA, before I go into what that acronym stands for, the original idea for VEDA before VEDA was an acronym was EO Lab in a Box. So that's Earth Observation Lab in a Box. So we basically wanted to use some of the ideas of MAP as well as this COVID dashboard that we developed. We wanted to use some of those components, but make them basically reusable for other science domains that NASA was interested in supporting. So that's why EO Lab in Box was the first term for that. But when it became an officially approved project for us to take on, we came up with this acronym VEDA, which is VEDA, or Visualization, Exploration, and Data Analysis Platform. And the vision for VEDA was basically to, quote unquote, accelerate the science lifecycle. So VEDA is not just a science development hub, it is also a dashboard and a data system. And it's not just one platform, it's something that can be basically replicated for other science domains. So for the VEDA project, we partnered with 2I2C. So 2I2C is an organization that deploys and manages Jupyter Hub environments. So 2I2C has taken over the Jupyter Hub development for Veda, for core Veda, as well as like Veda instances. So Veda is being replicated, and now we'll see a few more Jupyter Hubs. They don't need to be proliferated indefinitely, but we will probably have multiple hubs for these different science use cases. So we have the primary Veda platform, which has a hub that's open to users. And the MAP users, the multi-mission algorithm analysis platform users, are going to be migrating over to use that hub as well. And then we have a hub for our Greenhouse Gas Center instance. So the Greenhouse Gas Center, which is a website platform that NASA also runs, is based off of the Veda architecture. And then there will also in the future be other portals, such as disasters and air quality. And so those will also possibly have their own hubs as well.
And by the way, what is Development Seed, and how do you guys fit into this?
Oh, yeah. Good question. So Development Seed is a geospatial software services company. We are for-profit, but we are mission-driven. So we contract with NASA, and we've been working with NASA on contracts since a little bit before I started. So probably like 2017 or so. And so we work with NASA to help them basically modernize their Earth observation data systems. But we also have arms that work on machine learning and front-end development. Well, our front-end development also works with NASA on this Veda project. So we're basically a team of about 60 software engineers and designers that work on contracts with organizations and agencies like NASA.
Gotcha. So let's talk about the components of Veda a little bit. And you talked about some of these already. So like the Jupyter Hub is part of it. You mentioned dashboards, which are pretty interesting. So kind of what is that? And then like the kind of data API layer to this thing.
Yeah. So I usually break it up into three major components, which is the front end component, which at the moment consists of the dashboard, and then the Jupyter Hub component. And then both of those are sort of the end user interfaces into the data. And then so the third component would be like the data system. The data system comprises both the data APIs as well as all the data storage, right? Metadata and archival data itself. So those are the three major components. I will also mention at this point that, hopefully this is interesting to your audience, but basically the dashboard has right now like the very typical exploration and analysis type of map interface for exploring data and making little charts, etc. But one thing that we found is that depending on the users of this type of graphical user interface, they might have very different interactions that they want with the data, and depending on the data and the type of user. So one place that Veda is going very proactively is to developing more custom interfaces into the data.
And you are kind of bridging across multiple data archives, right? Like you mentioned sort of specific examples, but you have to interface with a lot of archives that you don't control to make this thing useful for scientists, right?
That's right. NASA has 12 different data centers that are all experts in the data that they manage, and they are producing, multiple data products per mission, many data products per mission. So we don't always have control over those data products, but we can control how we basically catalog them and bring them in. So we want the users of Veda to have access to all the data that they want to have access to do the exploration or analysis. But we don't want to maintain copies of the data, right? And so typically to do things like dynamic tiling of data, we will provide, we might provide a service to transform the data from its archival format to like a cloud optimized GeoTIFF so that we can do dynamic tiling on the fly. But we're finding that there's basically new ways to index into those data sets that mean we don't have to like reformat and create a new data product. So that's on this sort of like archival format side of things. Like we want to be able to basically interact with those. If the data is already on a commercial cloud system, we want to provide cloud optimized access into it. So that's why we're creating what we call virtual layers to enable basically subsetted access into that data by creating these like manifest or indexes. I don't need to go too much into the weeds here, but basically it just means that like we have you can think of like a table of contents into any particular data product so that you can just go to the page that you need and you don't have to like download entire files, if that makes sense. So we're doing that, but also to your point, we have lots of different data sources themselves. So we also index into our stat catalogs different data sources like data being managed by a different, a data center that's not cataloged by NASA, or another example would be like a climate modeling community, or a data set on AWS's Open Data Registry is another example. Even data sets that are managed by NASA has an agreement with has a project with Esri called Enterprise GIS. So even some of those data layers are being brought into Veda because users want access to them. So yeah, just to say we're plugging in lots of data into our stack catalog is basically the simple way to think about that.
Yeah, so if you just flip this around to the user perspective, what are the upsides that are bringing people into the Jupyter Hub, for example, to work? Is it like in large part that kind of layer making it easier to do their work? Is it the just like the other like cloud enabling things? Like how are you seeing people show up and want to use this?
I think direct access to the data is the big motivator, right? So like as opposed to working locally where you would have to like the network to get to those cloud files is like much greater. Whereas if you're working with the Jupyter Hub, like I like this saying, like data has gravity. Like you will want to work wherever the data lives, basically. So like if there's a Jupyter Hub that's in the same cloud, region, basically same building, if you will, like you want to use those resources. You want to use that compute resource over using a local machine or compute on a different cloud. Yeah, so that's a major pull in my mind. For MAP specifically, we curated a data catalog for those scientists. So again, data has gravity, but they were also pulled there because it had all the data that they were looking for to develop their algorithms in one place, in one catalog, I should say. So those are the two. That's the main thing is the data. I would say the other functionality that has been really powerful with some of these hubs is being able to create a container for your algorithm, right? So like being able to build a specific image, right? Like a Docker image for running your algorithms is also very powerful because then you can leverage parallelism with the cloud.
So what about the types of workflows that you see people building in the hub, or how you encourage them to use it in terms of like, are they kind of prototyping things and then switching somewhere else to run it at larger scale, or what's the use case been like there?
Yeah, exactly. So basically, the way that they've been using the hub, the map development environment, has been to develop an algorithm that works for doing some sort of predictive algorithm, right? Whether it's for estimating biomass or determining a fire perimeter, developing that on a small region. Once they're happy with that, they want to scale it out, right? So then they want to scale it out to the continental, the US or globally. And so then it just becomes a matter of basically parameterizing that algorithm and then running it on the data processing system, which can scale to like basically infinite number of workers using Kubernetes potentially.
Do you have folks controlling that from inside the Jupyter Hub, or are they kind of jumping to some other way of starting and managing that?
Yeah. One of the cool things that the JPL team built was basically a GUI for managing that. So it basically leads you through like how you need to parameterize your algorithm. It leads you through how to parameterize your algorithm, and then basically you publish your algorithm. So all these steps of like publishing and running your workflow have now all been integrated into the Jupyter Hub as like plugins. So you like develop your algorithm, you publish it, and then it becomes an image, right? And then once it's been published successfully, and there's some validation checks and stuff that go on there, of course. Once it's been published successfully, then you basically can pick it from a drop down of algorithms, enter the parameters that you have for your particular run. Like say, like, you know, your parameters are things like geospatial bounds or something. And then it will pick that up and it will run it in parallel. Yeah.
What about you internally? How have you guys been using the hub yourselves?
Yeah, so I've been mostly focused on the Map Hub or the map development environment is what I've been talking about so far with the scaling. My team is a team for Beta that's like the research and development team, and we're focused on optimized data delivery. So we've been using it to develop these virtual layers, like I was mentioning. So we, for these virtual layers, need to basically read the metadata from like, you know, thousands of files to create these indexes, which can be used by future users to make their analytical processes like faster because we've already indexed all of the data. So I've basically been using the hub to develop those virtualization steps of reading the data and combining those indexes into one massive index. I usually prototype those on the hub, and I could, in theory, use Dask at that point, but I'm personally a fan of lithops, is a lot easier. So I then would like execute a lithops job to build the index for the whole collection.
So we've been talking about kind of scaling things for parallelization here a lot, but I know you've thought a lot about, like as we have, about open science and reproducibility and the kind of services this might provide for those sorts of goals. So, I mean, what's your thought process of how this is going to be used in that way?
I mean, I think containerization is the big thing there, right? So once you've developed an algorithm that you're happy with and you know the libraries that it requires and like can pin the versions, you can create a container that can hopefully be run on like any of these hubs to reproduce that science, right? And yeah, I mean, I think the vision there at the moment, although I'm not like at the forefront of this, but the vision there at the moment would be like, yeah, you can basically port your image for running the algorithm to different Jupyter, like depending on what you have access to, right? Because it's like, oh, right now you're funded by this project to work on this hub. But let's say next year you're funded by a different project to work on a different hub. You don't want to have to like rewrite your entire workflow. That's why I think, 2I2C is great that it's managing a lot of these hubs, but just like having Jupyter Hub is kind of almost like a de facto standard at this point for algorithm development, like in Python. Yeah, that's really a goal there. And then I think the other piece of it is that if we're sort of standardizing on things like Python and some of these libraries, like you could, when publishing an algorithm or publishing a paper, like part of that whole ecosystem would be to like contribute the notebooks and then have the notebooks be something that either are like automated, like there's some automated system to say, hey, yes, this result is reproducible. But even more than that, what I think would be more, I mean, that's cool, but I think what's even more exciting or powerful than that is that people can build off of that, right? So it's like you published a paper on, the fire perimeter in California, but now I want to apply that to fires in India. Like I might need to make some tweaks. I can reproduce your science, but then I can like take it over to my region of interest or my temporal extent of interest, and I can like tweak it and build off of it. And that's why I think you see a lot of success in like machine learning, right? Is like a lot of those algorithms that are being developed in like Kaggle competitions or something, like a lot of those machine learning models, you can just like re-implement them and build off of them.
So what about on the onboarding side for the folks who aren't like just dropping in as wizards at this stuff, but are learning about it, or at least learning about like your hub in particular and some of the some of those things. There's a lot of resources that are out there, and how much are you having to create for yourself, and then how are you helping scientists who are trying to figure out how to do something?
Yeah. I mean, we have a really great docs hub that should help people get onboarded onto the hub itself, as well as how to use some of the APIs that we have. And so we try and put a lot of documentation in there in terms of how to use the hub and the data access pieces of that are sort of specific to the hub.
And then in terms of scientists coming in that maybe like know what their goal is, know what they're trying to do, but aren't quite sure how to get it done. You've been working like directly with them, right?
Oh yeah, yep, yeah. That's another point that I wanted to make was basically we have these science enablement teams. So I mentioned previously about how we have these above ground biomass researchers and also like people working on fire perimeter development, algorithm development. So they don't come to these hubs like obviously we have the documentation to support them, but they often are trying to do things that are going to be outside the scope of that documentation or like things that we don't expect. So the documentation is never going to be comprehensive, right? And that's why we like advocated for and now have this science enablement teams. So the scaling that was done on those algorithms I mentioned previously was done in collaboration between the scientists and the science enablement team as well that could sort of support the users in learning how to use the scaling system, the data processing system.
So this data processing system that you mentioned, like what exactly is that doing for researchers? How do they take advantage of that?
Yeah, absolutely. So they develop, they're usually developing an algorithm like just, in memory in a notebook that can work for a relatively like small region of interest, right? Because it's just whatever memory they have access to. And so what we provide for them is to support them in basically parameterizing that algorithm so that it can be run on the data processing system in parallel. So what that happens, right? Like the algorithm gets packaged up with the algorithmic code gets packaged up with its requirements file as an image, but a parameterized Docker image, right? So its runtime takes certain arguments that enable it to be parallelized across workers. So the DPS system and the interface that we've developed in Jupyter Hub to support the users walks you through basically creating that package, that algorithmic package. We just call it like publishing the algorithm. And then once it's published, right, it's in this registry. And so then you can look it up and execute it. And so you look it up in like a drop down, and then you add some parameters for running it across like many workers, basically. Yeah.
Gotcha.
And another cool thing that they built was a way to monitor your jobs in the Jupyter Hub as well. So that's obviously very important. That was something that was lacking in some of the first iterations. Was like, okay, I executed my job, but now I don't know what's happening. Like what happens next. And so, yeah, another really important piece was this like monitoring piece and bringing that into the Jupyter Hub as well. So you can like see your jobs, see how they're failing, and like iterate.
So it seems like cool stuff to help you bridge the jump from the prototype to the big run.
Exactly. Yeah.
The last thing is just like what's next for this project, or what area are you currently focusing on building out?
Yeah. So one we're really excited about, and NASA's also really excited about that I mentioned briefly, is these virtual layers. So basically a lot of the archival file formats that NASA produces data in was not designed for cloud-based access. So we are working on building out more virtual layer support for all the heterogeneous data that NASA manages so that people can access just the subsets of data that they need without having to download data. So you can think about this as having access to an entire logical data set without having to think about files, right? So you just say open data set and you have the entire collection's extent of space and time. So that's one thing that I personally, but also NASA, I believe, is also very excited about that direction for their data because it means they don't have to like reproduce everything in cloud optimized formats. It can still be in its archival format, but have this cloud optimized access. So that's one area we're really excited about. Beta as a whole, I would say, is also very excited to support some of these Earth Action instances. So Earth Action is an initiative at NASA to basically support more decision makers with Earth observation data. So we're supporting that initiative with more of these instance portals for different domains. So things like disasters and air quality, which I mentioned. As well as an Earth Information Explorer, which of course is sort of jumping on this bandwagon of LLM's development. So we want to help just everybody understand Earth observation data. So we're also working on that. Working on a lot of things, as you can tell. And then finally, with it, when it comes to the hub itself, like the Jupiter hub, they've been doing some really cool work when it comes to both allowing people to build their own images. So just throwing in a requirements file text, and so that you can build your own image, as well as like cost monitoring is very important, of course.
Yeah, cool. Well, it's super interesting to hear about this project and see, things that are similar to what we're working on, things that are like different and we never would have thought of or whatever. It's really cool. And I already kept you longer than I promised I would, so I'll let you go. But I'll put links to a lot of the things that we talked about. They came up in the video descriptions. You can go click on those. You can learn more about some of these things and check out some of those tools for yourself that are out there. And just as a reminder, you can find more information about our own project here at Earthscope on our website at earthscope.org/data/cloud. So thank you again, Amy.
Yeah, thank you.